premise of this presentation is that space-time is a momentary entity caused by universal expansion. Originally, space-time was a mathematical concept combining space and time into a single entity, space-time. Today's most popular concept of space-time is the one described in Einstein's special theory of relativity. In this theory, velocity dilates time and contracts length. It all goes back to James Maxwell. He did some fantastic work with the electric and magnetic field, and he realized that light was an electromagnetic wave, and as such, a wave needed a medium to propagate through. So he proposed the ether as this particular medium. Scientists realized that the ether couldn't be a carrier of waves. It could be a frame of reference for the Earth's motion through space. So by the 1880s, Michelson and Morley built an interferometer to measure how fast the Earth moved through the ether, through space. As the Earth moved, the interferometer should have measured what's called an ether wind. Unfortunately, the interferometer failed to measure such ether wind, which created a problem. So scientists proposed that the interferometer arms were shortened in the direction of Earth's motion through space, but just the right amount, and they called it length contraction. And there is a formula for it. All right? But they never gave a reason why. They even assumed that the ether was stationary compared to the Earth. But it occurred to some scientists, Minkowski, Lorentz, Poincaré, that space and time could be combined into one. And Einstein extended this belief into what we call the special theory of relativity and published it. Originally, special relativity was developed as a mathematical concept. And Einstein warned us against using a physical concept, making it into a physical concept. But Minkowski interpreted space-time in geometric terms as 3 dimensions of space and 1 dimension of time. And a few years later, Einstein published the general theory of relativity. And general relativity assumed that orbiting objects follow a curved path because space-time is bent by matter, not because of gravity. And support for general relativity was found in the 1919 solar eclipse and the correction of a Newtonian orbital problem. You see, Newtonian mechanics accurately predicted planetary motion, but there was a minor failure, and that was Mercury's precession. And precession is the shifting of the point when planets approach closest to the star. It seems that Mercury's orbit rotated around the sun. Well, they measure the precession at 5.74 arc centuries per century. It should have been, according to Newton, 5.3 arc seconds per century. By applying general relativity, it came up 5.75. So 5.74, 5.75, it kind of said that general relativity was better than Newtonian mechanics. The problem was Venus. The measured precession of Venus is 2.04. The calculated is 10.75, 5 times as much. That's a problem. Well, scientists blame this problem on Venus' low eccentricity. In other words, Venus orbits almost a circle. It's only eccentric by 0.0070. So it's almost a circle as compared to Mercury, which is 0.21. But the problem with this is Neptune. Neptune has a very low eccentricity also, 0.0086. But if you look at the measured and the theoretical precessions, they're kind of close together. So that really didn't solve the problem. It just shifted the problem from Mercury to Venus. So going against Einstein's wishes, Minkowski interpreted space-time as a 4-dimensional fabric. I like to propose a different interpretation using a modern analogy. You see, a plasma TV screen, or any TV screen, is composed of pixels. And every screen has a set numbers of pixels per square inch, the pixel density of the screen. Now, we don't call it pixel density, we call it dots per inch, DPI. It means the same thing though. It's how many dots you have per square inch. So in my analogy, and that's only an analogy, keep that in mind, imagine you have a TV screen that can be stretched forever in 2 dimensions. There's only a few problems with this screen. It can be ripped. The pixel must not enlarge. The pixel density, the dots per inch, must stay constant. And pixels are dark, they're not lit. So continue with the analogy. If you stretch the screen, it doesn't rip. Since pixels can't enlarge, stretching the screen will create space between the pixels and lower the pixel density, the dots per inch. But we said the pixel density can't change. Therefore, new pixels must be created. During pixels creations, the new pixels momentarily flash, then go dark. So, for the sake of argument, let's call the flashing new pixels axions. Since axions are created simultaneously throughout the screen, when stretched, the entire screen flashes for a moment. Being they're identical, axions create identical light throughout the entire screen. So if the screen is expanded constantly at a high speed, the entire screen appears to be constantly lit. So let's apply this analogy to the universe. Universal expansion enlarges the universe by continuously creating space-time everywhere simultaneously. The pixels in our analogy are equivalent to space pixels, wherever they are, and the axions are space-time. So during space-time creation, it's not light that flashes, but time flashes for a Planck time, a very small amount of time, then vanish. But the space portion of the pixel remains. So space-time is a momentary entity caused by universal expansion. Let's unpack this a little bit. The universe is expanding at the speed of light. Well, there's some debate about it. Universal expansion may be accelerating, but let's say for the sake of argument, it's expanding at the speed of light. This expansion must stretch the fabric of the universe, whether you call it quantum fields, dark matter, dark ether, whatever you want to call it, they must stretch. This stretching in space-time creation must have begun simultaneously. And apart from enlarging, space hasn't changed since time began. We can see galaxy from way back, almost the beginning of time, and they look no different from the galaxy we are nowadays. And that implies that the universe maintains the density of this fabric constant. Now, since gravity affects time, if you move away from gravity, time creation must be constant. Therefore, space-time creation must also be constant, which cycles back to the understanding that universal expansion is constant. But there's a limit to how much this constancy goes. Energy seems to condense space pixels together. If it's a low amount of energy, we call these photons. At high energy, pixels and energy become intertwined into mass, into matter. So mass has more space pixels around it. And as atoms gather together, the number of space pixels around them increases. And larger bodies have a higher space pixel density around them. Not measurable, but they have more of them. So the area, the volume around astronomical bodies has a high pixel density. Now, universal expansion cannot stretch that area, the volume, at the same rate as empty space. Therefore, less axions, less space-time are created around astronomical bodies. And as you increase the mass, less space-time can be created, which means less time is created. Therefore, around large bodies, time dilates. As I said before, time is created by universal expansion moment by moment, simultaneously everywhere in the universe, obviously away from matter. After creation, each moment of time, Planck time, vanishes and is replaced by another moment. It's almost like a magnetic field appearing and disappearing instantaneously everywhere. But space does not vanish, it remains. And this enlarges the universe. Therefore, space and space-time are two different entities. Space is permanent, space-time is momentary. Now let's go back to Mercury's problem. Around the Sun, space pixels are very dense and universal expansion is slower. Because of its eccentricity, as Mercury approaches the Sun, it enters the space where universal expansion is slower. So at that point, Mercury decelerates a bit and changes direction a bit. And as it moves away, it re-enters space where universal expansion is faster and returns back to normal speed. Does Mercury decelerates near the Sun and accelerates away from the Sun? No. Approaching the Sun, the acceleration lessens. And when it's receding, the deceleration lessens. In a way, it's no different from light crossing into a denser medium, whereby it slows down and bends. And when it comes out, it instantly speeds up and bends back to the original direction. Of course, light doesn't have any mass. It can't do that. It can't go back to the original direction. But Mercury has mass, and therefore it can't return to the same direction anymore. Therefore, it precesses. Now, if you go into Venus, in Venus orbit, space is denser and universal expansion is slower. Therefore, Venus moves slower, but at a constant rate. If you go to Neptune's orbit, space is thinner. Therefore, Neptune moves faster, but again at a constant speed. See, our theoretical models don't compensate for this difference in density or universal expansion speed. So, cherry picking here. Look at Venus. It has a precession of 2.04, eccentricity of 0.0070. If you go to Neptune, its precession is 0.036. The eccentricity is very low also. Now, let's take a look at Jupiter. It has a precession of 6.55, an eccentricity of 0.489. Uranus has a precession of 3.34, an eccentricity of 0.0473. Watch what happens. The eccentricity is the same, but as you move further from the Sun, the precession decreases. Same thing with Jupiter and Uranus. Eccentricity is almost the same, but as you move away from the Sun, the precession decreases also. So, summary. In Einstein and others, space-time was a mathematical entity without physical meaning until Minkowski changed it. Because of its expansion, the universe must create space-time axions in order to maintain a constant space density. After these axions are created, time flashes away from space-time and vanishes, but space remains, allowing the universe to expand uniformly.